Welcome back, student. We are seeing today the Thevenin theorem. We are going to prove the Thevenin theorem in the lab. So what is Thevenin theorem? So for that purpose, we need to find out the objectives of this particular experiment. To determine the need of network theorems in general, determine the Thevenin equivalent circuit of a given circuit, and then to verify the Thevenin theorem by comparing VTH and RTH values actually measured using formulas, and then those values that are obtained by analyzing the circuit in a lab. So we are going to make their comparison, and then we are going to get the results. So note that the results will be not exactly same, because theoretical we are taking the resistances reading as it is, while in case of practical the resistances tolerances get included in that. We are getting a variation in the readings, but it is approximately equal to the VTH and RTH calculated by using formulas as well as by using the lab circuit, or we can say analyzing the circuit. As you know the Thevenin theorem, so Thevenin theorem tells us that any two linear bilateral network can containing different voltage sources, current sources and resistances, we can have a very short circuit, we can say a very small circuit. It contains only a single voltage source VTH and a single resistance RTH. So let's look at here. This is what we can say circuit. It contains voltage source V as well as resistance R1, resistance R3 and resistance R2. So what we are going to do, we are going to perform this experiment in lab to calculate actually VTH and to calculate actually RTH. So before we have to find it like using the formulas to find out the value of VTH. So for each circuit the formula of the VTH will be different. So what is the formula of this particular VTH? So if you have to calculate the voltage VTH of this, so the equivalent circuit is like this. You will have a VTH and there is a resistance called as RTH. So this is VTH, Thevenin equivalent voltage source, RTH, Thevenin equivalent resistance. So this VTH is actually calculated across AB, right? VAB, you can say VAB. So it is calculated like this. So for that purpose, the current is flowing from this R1 terminal. Okay, it will go into R3 terminal and again going to the negative. Here is a loop. So current will flow in this loop only. There will be no current because this branch is floating. So we are going to neglect the R2 in here for calculation of the voltage. So that VAB, that part is nothing but now we are going to calculate it from this point. We are going to calculate the voltage actually across R3. So you can look at here, if the circuit is modified, it becomes resistance R1 and then the resistance R3. It is connected to ground, means negative, and here is a plus, or we can say this is a plus, this is a negative. We are having V. We are going to calculate the point A in here and the point B in here. So can you name the circuit? This circuit is nothing but a voltage divider network. So according to voltage divider network, VAB, that is also called as now VTH, it is to be calculated like this. Resistance across the resistance R3 divided by total resistance is R3 plus R1 multiplied by the supply V. You can see here the VTH formula is V to R3 divided by R1 plus R3. So R1 plus R3 is combinedly to be calculated as a total resistance, and then the R3 divided by total resistance into V, it will give us a H. Now calculation of RTH. So how the RTH is calculated? So for that purpose we have to short the socket. So by shorting the socket we are going to calculate RTH. So you can see here, if I short the socket by removing the voltage source, what will have the terminal R1 and terminal R3 get connected on one side, as well as on the other side they are getting connected, means they are sharing the node, means we can say R1 and R3 they are in parallel. So for parallel combination, R1 into R3 divided by R1 plus R3, this will be the formula for calculation of equivalent resistance when they are in parallel. And then if we calculate the parallel resistance, this resistance is there R2, so that resistance comes in series, we can have a formula plus R2. R1 into R3 divided by R1 plus R3 plus R2, this will be the RTH. So now in this case we are getting open circuit voltage VTH and equivalent resistance RTH. So now what we are going to do, we are going to find out theoretically what is VTH, theoretically what is RTH, Then by doing the practical, we can find out what is the value of Thevenin voltage in the lab as well as Thevenin resistance. So for that purpose, we are going to take a circuit where this particular resistance is actually the combination of them. We have 100 ohm, 330 ohm R2 and 680 R3. We are keeping V in volt constant to be a 5 volt. If we vary the voltage, the combinations will be more and more. So I am keeping 5 volt constant. R1 combination is there, 100 30 680, 220 330 680, 220 100 680, 220 100 and 470. So what we are going to do, we are going to calculate VTH first, it is expected. Then we are going to calculate RTH, it is expected. So you can look in here, when we take V is 5 volt, R 100, R2 330 and R3 680. So by putting in the formula of VTH, we'll get the voltage called 4.3589. So you can pause the video, just write down all these readings in your notebook and then complete the observation table, and then only you understand how this values comes from the formula. So for next combination 220 ohm, 330 and 680, we are getting 3.777 volt VTH. For the next combination of 220, 100 and 680, we are getting again the same combination as the resistance actually you can see in this diagram resistance R3 is changing from 330 to 100, and in the formula we are having only R3, R1 and R3, that's why the reading same comes. You can see here for the next combination 220 100 and 470 we are getting 3.405. so you can see here we are getting a reading 4.3 3.7 3.7, same as there is only R1 and R3s are there, so we are not having R2 that particular VTH formula, that's why if R2 get changed the value remains same. Now, in case of resistance calculation, so we required only resistances 100, 330, 680. If we do the calculation, you can pause the video and just write down the calculation in your notebook. 417.17 ohm. So for next, it is 496 for this combination. For next combination, we are having 266, and for this combination, we are having 249 ohm. So I am going to write all the VTH expected, all RTH expected, and then I am going for the voltage measurement and current resistance measurement in a lab. So we are keeping V1 as 5 volt constant. I'm going to shut down and I'm going to make the connection. So I'm going to connect the plus voltage to the input of this particular socket. The ground terminal should be connected to the ground. We have a combination 100 220 at R1, 330 100 at R2 and 470 and 680 at R3. So we can have very much possible combinations. So in the first combination what we are going to do, we are going to connect the resistance R1 as 100 ohm, then we are going to connect the resistance as 330, so that should be connected to the V output, and the last, so we are going to take another one cable, we are going to connect the in ground and 680. So this is the combination 100 ohm, 330, 680. We have to make the DC regulator on. So I am making the circuit on. So let's look at here what I have to do. I have to connect the multimeter in between the output and the ground, and I'm going to measure the voltage. You can see here it is 4.4 voltage DC voltage, so we can see it is a VTH Thevenin voltage. So to measure RTH I have to just disconnect the power supply and I have to short the R1 with R3 so that the supply is just removed, and we are going to measure a very equivalent resistance or RTH. So I have to make it to resistance terminal 0.421k. So it is 421 ohm actually, or we can say 0.421 kilo ohm. So this is the way we can measure VTH and RTH for one combination. If you have to do the next combination, I am going to take it to be as a 220 ohm. So similarly again we are going to connect to the power supply. I am going to measure the DC voltage, so I am going to make it on. Now you can see here the VTH is to be seen 3.81. I'm going to make it off. I'm going to connect or short the R1 resistance with R3. Going to put it in resistance measurement, so it is indicating 0.498k or 497k. So it is 498 ohm or 497 ohm. So we can do it again for the next two iterations. So I'm going to make the supply on. So for that purpose we need to change the next combination. I'm going to make it R2 as 100 ohm. What we need to put it into DC, and we need to connect the resistance to 22 again input side. So we are measuring VTH, so it should not be shorted. So it is 3.82 volt. Now for the resistance we are going to remove the supply. We are going to short the R1 with R3, and then the resistance measurement is showing us 0.274 kilo ohm, or we can say 0.275 kilo ohm. So it is 274 ohm or 275 ohms. So for the next iteration, what we are going to do, we are going to connect the resistance to 470. We are going to make DC voltage, remove the shortage, connect it to input, make the circuit on, power supply make on. We are getting 3.39 DC volt. And for the resistance RTH to be measured, I have to short R1 and R3. Then we are getting resistance when I shift selector switch to resistance 0.257 kilo, 257 ohm. So you can see here I have written the measured voltage as well as the measured RTH over here. So you can see from this the expected and the observed are measured. It is approximately equal. This is due to the fact that this is actually the theoretical readings. These are the practical readings. You can see the practical readings are little less or little more. In this case it is more, right? This case it again it is less. So you can see a little more or little less, that is depending upon the resistances, tolerances. That's why we are getting the different reading. So you can see in a resistances 417 here, 421 in here, 496 in here, 498 in here, 266, 274, 249, and you can see here. So from this particular readings you can see here we can have a Thevenin theorem to be proof. So this socket, actually this socket and this socket showing us the same result, giving us a same reading at A and B, the resistances as well as the voltage at AB. So in this way the Thevenin theorem can be proved.